This video is an effort to help users create scientific imagery which will look optimal when copied and played on a videotape. It will help you choose color combinations, text sizes, and other image characteristics for avoiding pitfalls. Consider the suggestions made in this video as guidelines only, since determining image quality is a very subjective process. With this in mind, we will begin by looking at an animation of a rotating globe with simulated data contoured over the surface of the continents. Notice the distracting flicker along lines of latitude and longitude. This is caused by video's interlace scanning technique. Also notice how difficult it is to read the text and how some colors like the reds and blues tend to bleed into the surrounding areas on the video. Although many of these problems are simply inherent to the videotape medium, there are steps you can take to minimize them. We will offer suggestions of better color combinations later in the video, as well as tips for maximizing the useful area in the image. Users are often disappointed when they compare the output from a VHS videotape with the original display on their computer workstation. One of the first things they notice is that the videotape image seems much less clear and crisp than the original image. In particular, labels that were clear on the workstation may appear muddled or even unreadable on video. This is due mainly because NTSC video has a very low resolution compared to computer workstation video. We will discuss the limitations of video resolution next. Video imagery looks worse than the original workstation display because the image resolution is reduced when converting digital imagery to video signals. Once you have your imagery stored in an image file, it is sent to a video system like NCAR's text and graphics system, TAGS, for processing. The video system resamples or resizes the image so that its dimensions are 640 by 480. We recommend that you create your imagery with these dimensions to begin with and therefore avoid possible resizing and resampling problems like image distortion and clipping. Depending on the type of video format you would like, the image is then converted into an NTSC video signal and fed into the recording device of your choice. VHS, U-Matic SP, SVHS, or Betacam SP. The video recording device then records the signal onto a videotape one image at a time. The different video formats, however, impose different resolution and quality characteristics on the final product. For example, the resolution of a VHS image is only 240 by 486 compared to U-Matic SP, which is 330 by 486, or SVHS and Betacam SP, which are both 400 by 486. Betacam SP, however, has much higher color resolution. Currently, the highest quality videotape format supported at NCAR is Betacam SP. Video quality and resolution are at their lowest when using the VHS video format. Unfortunately, VHS is currently the most common video format and is therefore most often the format of choice when creating videos to show at conferences or share with colleagues. However, no matter what video format you choose, your video image will never look as clear as your original digital imagery because of the reduction in image resolution and other video limitations. A common pitfall encountered when copying digital imagery to video is the problem of image clipping. In this example, some of the text at the top and bottom of the image is too close to the border. This text may be clipped by the video monitor if it is not within the safe image area. The safe image area is the rectangular area of an image that is safe from being clipped. The distance between the edges of the safe image area and the image border are measured as percentages of the plot or frame width. In general, all text and image components should be placed 5 to 10% in from each side of the image to reduce the possibility of clipping when played on a consumer monitor. Therefore, our first correction to the globe animation is to move all parts of the image well into the safe image area. Since we have plenty of room on both the left and right sides of the image, we only need to lower the text at the top of the image, raise the text at the bottom, and shrink the color bar. Because of the way colors are encoded in a video signal, combined with the human eye's sensitivity to different colors, some colors appear sharper than others. The video signal was designed to carry more yellow-green color information than red and blue. Grayscale imagery, however, has the highest resolution and is therefore the sharpest. This means that yellows, greens, and grays appear more crisp on videotape, and reds and blues tend to bleed into the surrounding regions of an image. Therefore, it is also important to avoid certain color combinations when labeling an image. As you view this series of images, notice how the readability of text depends on the color combinations in use. Some combinations work well and others make the text unreadable. In particular, blue and black or yellow and white combinations are poor choices. Also notice how the red and blue characters are generally much less sharp than the green, gray, or yellow characters, depending on the background color. Also note that you are viewing a VHS recording. With higher quality videotape formats such as Betacam SP, the color resolution is greater and the characters would appear more clear. The remaining examples complete the set of color combinations which you may find useful as a reference. After examining the previous text and background color combinations, it's obvious that the blue text on a black background is difficult to read. Therefore, our next improvement will be to change the text color to white, which shows up better on a black background. Because videotape resolution is so low, it's important to maximize the useful area in an image by removing non-essential objects. In this animation, it isn't necessary to include the experiment number or the title on every frame. The image would appear less cluttered if we moved the text to a separate title frame which was displayed once at the beginning of the animation. Since the date string changes during the animation, we will leave it in the image and convert it to a 3-character abbreviation so that all date labels will be the same length. This makes the date label less distracting as it changes. Also, we will add a variable label so viewers will know what simulated data is being displayed. This series of examples demonstrates how text readability changes depending on the text size and aspect ratio. The sizes displayed represent the character width as a fraction of the frame width. Notice how small text becomes more readable as the aspect ratio increases. Text size needs to be relatively large in order to be readable on a videotape. As a guideline, we recommend using characters with a width that is at least 3% of the width of the frame you are rendering into, and an aspect ratio, width to height, should be at least 1.75. The text in this example is too small to be read easily, so the next improvement will be to increase the text size to make it more clear. Another common video problem is that images that contain horizontal lines that are 1 pixel wide tend to flicker, as you may be able to see at the top of this example. Horizontal lines that are wider, however, do not. This is caused by a video technique called interlace scanning. With interlace scanning, an electron beam scans horizontally across the screen and displays odd-numbered lines on one pass and even-numbered lines on the next. Therefore, lines that are only 1 pixel wide are only displayed on every other pass, which we perceive as line flicker. This problem is especially obvious when several horizontal lines are displayed together as in these example grids. Notice how the grid with 1 pixel wide lines on the left flickers much more than the grid with 2 pixel wide lines on the right. To reduce line flicker in your imagery, we recommend using horizontal lines that are at least 2 pixels wide. Also notice that interlace scanning only affects horizontal lines. Lines at other angles do not demonstrate this effect regardless of their width. Therefore, the next improvement to the example image is to set the line width of all lines to 2 in order to avoid the problem of line flicker. Lines, however, can also contribute to chroma, which is a shimmering caused when the video signal changes abruptly. In our globe, we have several sets of lines which clutter the image and contribute to chroma. Latitude and longitude lines, contour lines, and map boundary lines. We recommend removing outlines to simplify the image. As we remove them, notice that the shimmering along these lines is greatly reduced and the image appears less cluttered. The drawback, of course, is that as we remove the lines, we also lose some information, such as what countries the contours cover. Ideally, we only want to remove the non-essential lines and keep as much essential information as possible. Another way to reduce chroma when working with contoured images is to use smooth contouring. This example demonstrates different methods for contouring and text reduction with a recommended method on the far right. On the far left, we have discrete intervals that represent the different contour levels in the contour plot. However, on the far right, we've made the change between adjacent contour levels smooth. With smooth contouring, the video signal will not have to change abruptly between contour levels, and therefore the amount of chroma will be reduced. Also, as you move to the right, the labeling has been simplified in the last color bar to reduce the amount of text, and a percent sign has been added to the labels to specify the variable units. Now, if we apply the smooth contouring to the contours themselves, we will get an image with a lower amount of chroma. In this image, we've increased the number of contour levels so that the change between adjacent colors is smooth. Although there are many more color transitions, the transitions are less abrupt and therefore there's less chroma. Also, we've simplified the color bar labels and added a percent sign to specify the variable units. Another way to reduce chroma in a video image and to a lesser extent color bleeding is to lower the saturation level of your colors. As you can see in this example, where we are using a hue saturation and value, or HSV color model, some colors appear more crisp than others depending on the level of color saturation and color value. Color bleeding in chroma is less noticeable when the saturation levels are lower. As the example continues, you may notice a color shimmering effect, especially in the areas of high saturation. In order to minimize this chroma, we recommend using colors with a medium to low saturation value. If you are using an RGB color model, you can control the saturation level by scaling the RGB values by a constant. We recommend scaling the values by 0.75. The final correction to make to the video image then is to lower the saturation level of all the colors in the image. In contrast, the original image looked like this. Again, notice how hard the text is to read and the amount of chroma crawl. The first correction we made was to move all the text and imagery to within the safe image area. Then we chose a text color which showed up better on a black background. We removed some of the extraneous text and added a variable name. We enlarged the text to make it more readable. We increased the line width to eliminate horizontal line flicker. We removed lines in the image to reduce chroma crawl and clutter. We simplified the color bar labels and used smooth shading. And finally, we reduced the level of color saturation. Now let's look at the animation again, but this time with all of our changes applied to the imagery. We begin by including a title frame for the text that doesn't need to be repeated on every frame. Again, we want to stress that the suggestions which were made for improving this imagery should be considered guidelines only. What looks good to one person may have no appeal to the next. Also, it's important to remember that with current video technology, your video imagery will never look as good as it does on your computer workstation, mostly because of video's low resolution. Often, the best you can do is minimize the effects, as we have tried to demonstrate here. For more detailed information about creating video animations at NCAR, you can order the NCAR SCD user doc entitled A Guide to the Production of Computer-Generated Video Animations Using Tags. Also, this video is available for ordering.